Welcome to the Chapter 8 for Math 31, Exponential and Log Functions, the review and preview. And it starts with, honestly, some stuff that you should already know. But, it's valuable to look over. It's in your textbook as well. But just talks about some of the different exponent laws that we've used throughout the years. Really important that all of these they have to be internalized, so you can't be, they're not on a formula sheet anywhere that I've seen. You really have to know how to use these. We'll use them as we work through the examples, but some other stuff that we're going to look at is logarithms. Logarithms are pretty important. This is going to be a little bit of review. Well, I guess the title, you would guess that it's review, but definitely we do a little more in 30-1 than we used to. So typically students have told me that they find Chapter 8 just to be a little bit easier at this point. Sometimes students don't like looking at logarithms in this general form. So if I had that log base 2 of 16 was equal to 4, then the exponential form of this would be 2 to the power of 4 is equal to 16. Now, really importantly, these two things are saying the same thing. We have to get used to that. Remember that if you are not given the base, so if I told you the log of 1,000 was equal to 3, you have to remember that that's log base 10. Right, that's kind of maybe the default base of the logarithms that we use. Speaking of logarithms, there's everybody's favorite, which are the log laws. We have to know these. We are going to use these to manipulate not only logarithmic expressions, but exponential expressions as well. If you remember a little bit back in Math 30-1, the power log law, number 3 in this list, is, I would argue, the most powerful of these log laws. Pretty important about 1 and 2 is that they do have to be the same base. So if you had log base 2 minus log base 3, you can't do anything with that. We're going to look at manipulating a couple of these just so you can see logs in action again. And then certainly most of this assignment is just some kind of, just a check to make sure you remember how to manipulate and how to use the algebra in this section. So it wants us to use the laws of logarithms to rewrite the following. It should probably say rewrite the following as the simplest logs possible. Because the inside of the argument is what's in a bracket here, is multiplied, I can rewrite it as the addition of 2 logarithms. So log base 2 of 6x is equal to log base 2 of 6 plus log base 2 of x. Similar to that in B, there's actually a couple different ways of doing B. I'm going to do both of them here. Most students would immediately split the argument into both products. So log base 5 of x cubed plus log base 5 of y to the power of 6. We could then move those exponents as coefficients. So 3 times log base 5 of x plus 6 times log base 5 of y. The other method of doing this, which I want to show, would be to immediately rewrite the argument of that logarithm. I'm going to do it in red over here. We could write it as log base 5, and then within that argument, we could write this as xy squared cubed. And the reason we can get away with that is that power, right? Power and a power. Xy squared to the power of 3 is x cubed times y to the 6. That would allow me to take that coefficient out right away. So 3 times log base 5 of xy squared. I could then split the logarithm. So 3 times log base 5 of x plus log base 5 of y squared. I could then manipulate, so I'll put that square bracket again, the second logarithm as 2 times log base 5 of y. And then just to make sure that we do see that it's the same as what we got on the other, the blue technique, when I distribute that 3 onto both terms, I would get 3 times log base 5 of x plus 3 times 2 or 6 log base 5 of y. Right, no reason to do, the red technique over the blue technique, but I did want to show that there's more than one way of doing this question, or that question, sorry. For C, because you have a denominator, I would immediately split that logarithm into 2 different logarithms using our division log law. One of the things that we've been pretty consistent with in calculus, though, is not writing those radicals as indexes or as radicals, writing them as a fractional exponent instead. So I could change log AB to log A plus log B, but then I'm also going to write this third logarithm as the log of c to the power of 1/3, and then I can take that exponent out. And that's just kind of another reason why writing those radicals using fractional exponents does make some of this work a little bit easier. I just wrote an equals instead of a 1/3 there. Let me get that. So hopefully, you're not struggling too much with that. If you are, if you find yourself struggling with logs quite a bit, I would really recommend that you maybe take a look on my YouTube channel for the Chapter 8 material for Math 30-1. right? There's it's probably 2 hours total of videos, but maybe you go back and you look at solving with a logarithm or manipulating using the log laws, because there certainly are those videos online if you want to check that out. If you do want a copy of the notes or something like that to maybe follow along, just let me know and I can arrange to give that to you digitally as well. Okay, last part of this review and preview is why do we care? What is the use of the logarithm? And certainly A is just a logarithmic equation. There's nothing really to, well, it's important, but it's not really using the log. Question B is why we want to use the logarithm so much. You cannot solve B algebraically without the logarithm. And we're going to practice that quite a bit in the actual assignment contains quite a few of these. For part A, I can't really do anything with it as is. Now, one thing, there's a couple different ways of doing this. I'm going to write above that if I had the log of x equal to the log of y, the only way that's true is if x is equal to y. Now, there is no logarithm on the right-hand side, but I could write the whole number 3 as log base 2 of 8. And I want to show you that what that allows me to do is I could say that log base 2 of 25 minus x, I could write the whole number 3 as log base 2 of 8, because log base 2 of 8 is 3. And now that I have that log base 2 on each side, the argument of the left-hand side must be equal to the argument of the right-hand side. To solve this, I would subtract the 25. I get that negative x is equal to negative 17, so x is equal to 17. Now, one of the things that we will get into more in the notes is you cannot take the logarithm of a non-positive number. It is always worth checking that if your solution would cause that. If I put 17 back into the original expression, I would get log base 2 of 8 is equal to 3, which is true. Now, this is probably, I would say, not my favorite technique. There's nothing wrong with it, but I would prefer if we get used to or comfortable or proficient with switching from log form into exponential form. So if I have log base 2 of 25 minus x equal to 3, what I can say is that the argument, the 25 minus x, is equal to the base of the logarithm to the power of the value. And if I manipulate, or I guess expand that right-hand side, I get exactly the same thing I did right there. So black technique and the red technique are equal. I prefer the red technique, but it does require a pretty high level of comfort with switching from log form to exponential form. All right, all that aside, B is very, very important. All right, in Math 30-1, you learned another technique of solving exponential equations, which is changing the base. It's possible with a logarithm that we could write the number 7 as 3 to the power of something, although it would involve a logarithm. So typically, if we cannot change the base using an integer, like if I had 3 to the power of x plus 2 is equal to 9, I could change 9 into 3 squared and then solve that using exponential techniques. But because I can't write 7 in base 3 easily, we are going to instead use the logarithm with the intent of making the exponent a coefficient. And the way that we do that is basically the statement that I wrote in black right here in reverse. So think of 3 to the power of x plus 2 as x and 7 as y. What I'm going to do then is I'm going to introduce a logarithm on both sides. Now, you don't have to use that property to do this. The logarithm is an operator like anything else, and as long as we're doing it to the entire side, that's a valid algebraic step. The advantage to this, though, is now that exponent, x plus 2, can be made a coefficient. So it's x plus 2 times the log base 10 of 3 is equal to log base 10 of 7. Well, if I wanted to solve for x, what I would do is divide by log 3 on both sides. What that leaves me with is that x plus 2 is equal to log 7 over log 3. If you want to practice your logarithms, not a bad idea to kind of rewrite log 7 over log 3 as a different base logarithm, and I'll do that at the end here. I would then move the 2 over, and I get that x is equal to log base 10 of 7 divided by log base 10 of 3 minus 2. And I would like to point out that this log base 7 divided by log base 10 of 3 is log base 3 of 7. And you can find that log law on your log rules as well. I'll write it down. It's only going to take a second. I'm basically saying that log base b of the argument a is equal to log base c of a over log base c of b. You can make c anything you want, but don't use anything other than 10. Because that really allows us to evaluate something like log base 3 of 7 without actually needing a different base operation on our calculator. All of your scientific calculators and all the Texas Instrument calculators have log base 10, The one that we're going to use a little more in calculus is log base E, and we'll talk about that. I believe it's an 8.3. All right, so that is it for the review and preview. Make sure you're doing this assignment. It's really important you're comfortable with the logarithm. We are going to use them within calculus quite a bit. So the more comfortable you are, the easier basically this calculus section becomes.